Hello and welcome back. This is the second part in a series of Plan 9 lecture videos where I'll be talking about the design of the Plan 9 operating system. The first part, if you had missed it, it can be found on the channel. This time we're going to be talking about file-based abstractions. It's kind of what I think lends the most to how Plan 9 differs from Unix or Linux as it is today, and I think the core design of it influences a lot of how the design of the system kind of comes out of that. In order to talk about this first, though, we have to start back from the basics. Let's talk about system calls. Now, system calls, or syscalls shortened, define the interface to the kernel. You can kind of think of them as the kernel's API. In doing so, they kind of shape a lot of the overall design of user space. How programs interact with the kernel kind of tends to influence how they're written. They are tied to the assembly calling convention, so if you want to make a system call from C, usually have some kind of assembly stub. So even if you're making a system call from a higher level language, they'll either have to call into C, which is doing an assembly call, or they'll have to code in some assembly themselves in order to make this system call. It's in broad strokes, you can think of system calls as how a process interacts with the outside world. And a lot of how those interactions manifest is by dealing with I/O of some kind. You want to write to a file, you want to write on the network, you want to write to a pipe. A lot of what we're doing, a lot of programs really just kind of do that. They take in data, process it, or take data from the network and process it. So this ends up being a pretty important factor in the overall design. So let's talk about the file system as well. So a file system, abstractly, it's a tree of directories and files. Both are addressed through a path. Paths in Unix start at /, that's the root folder. Subdirectories use / as a separator, so if we're referring to dir C, which is in dir B, which is in dir A, which is in the root, this is what the path would look like. Conceptually, they're an abstraction on top of what's called what I'll call a flat disk. So you have one hard drive, that's your kind of big bag of bytes, and the kernel and system kind of take that and abstract a directory of trees on top of that. So it's being marshaled to a large disk. And as we learn, system calls are how we interact with the rest of the world, and the rest of the world includes our own file system. So system calls are going to dictate how our program interacts with the file system. So this is kind of a basic overview of the methods under which a program may interact with the file system. We have kind of these are based on what's used in Plan 9. These are not exhaustive, but I think they give a good idea. We have open and create, which either opens an existing file or creates a new file. Once it's opened, we can then read and write upon it, or we can seek. Every file as it's opened has a position internal to the kernel about where your current cursor is within the file. So if I open a file and I read 10 bytes, my cursor is now set to read the next byte, so byte 11, and so on and so forth. Same with writing. So seek allows you to modify where the current cursor position is within the file. Stat and wstat are respectively reading and writing metadata. This is all of the extra bits that's associated with the file. This is your permissions, your owners, your group, etc. And of course, when you're done with the file, you close it. You tell the kernel, I'm no longer using this resource. I'd like to, say that I'm done with it. So we can see here, we open and create, they return file descriptors. It's really just an integer. You can kind of think of it as generally a handle and opaque reference to a file. In reality, it's a integer index into an array within the kernel that represents how many open files a system has. Mode here also talks about what you're going to do with the file. So when you open it, you have to tell the kernel, I'd like to read it, I'd like to write with it, or I'd like to do both. This allows the kernel to do permission checking up front, a bit of an implementation detail. Just wanted to explain what that was. Permissions here in create refer to the actual permissions. Do you want read, write, execute by the user, by the group, by everyone else, classic Unix permissions. So everything we do with the file system, everything any program does with the file system is kind of through this core lens. So as an example of that, if you want to find out which files are in a directory, you open the directory file itself, and then you read it, and that'll give you back an array of meta information about its children. So that'll be its name, its permission, its owner, etc. You can use that to programmatically walk through the entire file system tree. So what really is a file though? Well, from our interface, we know a file really just is kind of a file descriptor. That's how you as a program interact with it. And really a file descriptor is just a thing that you can do read and write with. So you open some file, you can read it, you can write with it. If you can take something, open it, read it, and write with it, then it's a file. So, for example, pipes on Unix, they're first in, first out buffers, so they count as files. They're a thing that you do reads and writes with that you refer to as a file descriptor. Now, the semantics of what exactly that file I/O means, what's really happening when I read and write to a file, is not defined as part of the interface. It's more defined semantically by where it is in the path. So you have a dev SDA, that is a disk file, traditionally. So it's expected that programs that are interacting with that file have some knowledge about what it is under the hood. So we can kind of conceptually think of a file system as a mapping of strings, which is the path, to a thing that I can do I/O with. This gives us a really nice building block for building more complex semantics off of these core rules. Let's take kind of a first example, something that anyone that's used Linux or Unix might be more familiar with, which is your hard drive file. So on any Unix, your hard drive is expressed as a single file. That's your dev SDA, SDB, SDC, so on and so forth. So our file operations semantically map really nicely to what a hard drive is. What do you do with a hard drive? Well, you open it, you spin it up, you read it, you store data you read it, you read data off, you write to it, you store data on the disk, and at least is true with older hard drives, seeking could actually refer to seeking the physical head on the platter telling it where it needs to write next. Stat and wstat don't exactly apply here, they're not too useful, and of course you could say close. Well, I'm closed the hard drive now, I can now spin down the hard drive, we no longer need to use it. Oops, I lost my track here. Okay. So when we use dev SDA, because we have this file system mapping, this allows us to use any normal tools that interact with files, and we can use our disk file in place of it. So anyone that's burned a Linux ISO to a flash drive is familiar with this DD dance. You say, okay, read in distro.iso, write it out to dev SDC. And really, there's no magic in DD. DD doesn't know anything about file systems, really. It has a lot of tunables. You can tune block size and how much to copy and all these different things. But it's really kind of just a cat, like a lot of complexity on top of cat. So you could just as well as you could DD that, you could also just cat distro.iso directly onto dev SDC. That would accomplish the same thing as the DD command. Or for a more historical approach of how we use something like tar, you could tar up a directory, in this case mycooldir, and store it directly onto the USB stick. No file system there, no nothing. It's just a raw tar file. And of course then later you could extract from dev SDC all the same. This is essentially how tar was originally intended to be used. You would hook up a tape to your computer and then you would write out your backups using tar directly to the tape without any file system on top of it. Or, of course, if you happen to just store text in the USB stick without any sort of file system, you could just as well also use something like TR, translate lowercase to uppercase on the text file in dev SDC. All of this works without having any program here aware of what the hard drive is. It's just a bag of bytes. It uses it like it could use any other file within a file system. And also you know that there's no new system calls needed. Our core semantics here of our file system calls are enough to map everything that we need to do with this file. Now Plain 9 asks the question, how do we take this a step further? How do we take this abstraction and make it useful for more interfaces than just hard drives? So let's take a look at another example, TCP connections. TCP connections are semantically a thing you do I/O with. So, Unix, for this use case, decided to add new system calls. These are colloquially referred to as the BSD socket API, whereas, as I've alluded to, Plain 9 decided to use a file system abstraction in order to provide the interface for the network connections. So, for a brief refresher and people that haven't spent time with this before, this is how BSD sockets look like in Unix and Linux land. This is a truncated example taken from the get attr info manual page. We see here we're kind of taking our connection information from the arguments. So I believe the first argument is the host address, and the second argument is like the network type, or the port, sorry. So here we call getAddrInfo. GetAddrInfo is a libc function which will do DNS resolution. So if you give it a host name, it'll resolve that for you. And that will give you back potentially a list of results. So we have to loop over all results. We call socket, which is telling the kernel I would like to create a network object. And then you can call connect, which is saying, okay, I'd like to use this network object to now create a client-side connection. And so in this example, socket and connect are both new system calls that have been added to facilitate this feature. And of course, after we've called connect and we find our successful connection, we can then call read and write on the file descriptor as we would with any other thing we can do I/O with. It's not quite exactly like that. There's stuff like send and receive which complicate the matter, but for the most part you could use this interface like this without really much issue. And there are other system calls that were added as part of the BSD socket API, but for now we'll just focus on these two. Now let's compare it to what Plan 9 does. So up here at the top I have the libc wrapper that most programs that want to make a client-side TCP connection will use. We call it dial. It's not that large. It's roughly about 225 lines of C code used for all of the associating code in order to make this connection call. We see that we pass it this string. This is referred to as a dial string. It has three parts: the network, the host name or IP address, and the port. So our host name is translated by NDBCS. That's a user space file server, outside of the scope for right now, but just know that DNS translation does happen. Networks are served via file system. So here we're passing netTCP. That actually is a directory on the system that's expected to follow a specific convention in order to allow programs to create connections with it. So how does that actually happen? Well, first of all, dial will open the netTCP clone file. This reserves a new connection. This is the equivalent of calling socket on Unix. Once we've created our connection, we read that file, and that gives us back our connection ID. That connection ID maps to a corresponding subdirectory of netTCP. So we read back ID, we can then know that our connection is netTCP 10 or 12 or 25, whatever. So then once we have this file, we can then write to it and tell it what we want it to do. So in this case, we're connecting outbound, and for the sake of this example, pretend that google.com is located at 1.2.3.4. So after doing DNS resolution, the dial libc wrapper then writes the string connect, the IP address, and then the port. And this tells the file server serving this, it could be the kernel, it could be user space, that I would like to initiate this connection as a client-side connection. So once that's done and you return from that system call, now we can open netTCP ID data, which then allows us to use that data file as the main I/O for our connection. So this works for any protocol. This is not TCP specific. UDP or RUDP or whatever protocol you'd like is implemented exactly the same. This is not TCP specific. Now up front, this is a little bit more involved. There's a little bit more going on than just making a couple of system calls. There's a really good reason for why we design things this way. And in order to do that, I want to kind of illustrate more of an example about why this stuff is beneficial. First of all, it's very transparent to use from any sort of system. So you can also make TCP connections from your shell. So this is a little RC script that shows a basic example of opening a new TCP connection, getting RID, telling it to connect to another machine on my local network on port 8080, and then sending a hello string from my machine to the remote machine. RC doesn't know anything about network connections at all. It just knows how to deal with files. But because our TCP connections are made out of files, we can effortlessly use that interface from any sort of program that can interact with files, the shell included. In fact, Bash on Linux has something similar. They have a /dev/TCP, but it's implemented as a bit of a hack, because in order to do this, Bash actually intercepts the file path, so you interact with it, and is doing sockets and connections under the hood for you. So while it's provided this kind of nice interface, itself is not transparent to the actual core way in which a program interacts with the underlying kernel. So let's kind of expand a little bit more about how this interface is quite beneficial. So when you put it in the file system, you gain a lot of flexibility because file systems are something that is largely easy to deal with. Plan 9 has spent a lot of time and effort making it quite easy to manipulate and share file systems between hosts. So if you can expose a file tree, which we can do using something like exportfs, you can import a remote machine's network interface or expose your own network interface just by exposing the files. You can also combine multiple interfaces together to form kind of one merged interface. And in general, this is done because, like I mentioned, Plan 9 presents tools for making this happen. So if you can manipulate file trees, you can conceptually manipulate networks, which is a very powerful line to draw between these two abilities. So as a conceptual example, consider a VPN, a virtual private network. Those use a internet connection typically in order to establish a encrypted private network transport layer on top of the basic internet connection. So for example, you could connect to a remote machine and then provide a personal network on top of that that's encrypted. So in Plan 9, for example, if I wanted to write my own VPN, if I wanted to implement something like WireGuard, I could have it work by using /net to create the connection, and then the VPN could expose a /net for that connection. So anything using that /net would transparently use just the VPN and the VPN alone for making these connections. And you can kind of choose which programs are under that VPN by using namespaces. This is all quite nice things, I find. So here are some practical examples talking a little bit more about how you would do something like this. So like I mentioned, we can import file trees from a remote host. That's what this R import is doing. We can say, okay, take the /net from my host, put it on our /net, and then let's use it. We'll use aux_listen1. This is a basic listen on a TCP connection and execute a command with the connection on standard in and standard out. So we listen one, we say, okay, listen on port 8080 and run our HTTP server. This actually listens on the remote machine, something similar to SSH forwarding. Without having any programming or anything, without having to allocate local forwarding ports, this just works. And no, that program doesn't have to have any information about the fact that it's using a remote machine at all. It's all transparent because we use this file-based abstraction. So you can do something a little bit more complex if you wanted to. This is kind of the example I talked about merging. So we could import two different machines. And I want to use one machine for TCP and I want to use the other machine for UDP. We can simply use bind, which replaces one part of the file tree with another in this case. So we can say, okay, if we're calling that TCP, use my host. And if we want to use UDP, use my host too. This all kind of naturally falls out of this interface. So some other file-based examples that I think are quite nice in order to kind of further illustrate how these interfaces work. We have a QCOW-FS. This takes a QCOW2 disk image, which for those that are not familiar, it's a way of representing a larger disk, so like a 100 gig or 50 gig disk, but only storing what's actually written to it. So it's used quite often with things like virtual machines. So QCOW-FS will take the QCOW file and expose through the file system a disk file that represents the total actual size of the disk. So any program can take use of QCOW without having to actually bind it to any libraries, without having to know how the QCOW-FS works at all. And this allows us to make, for example, our virtual machine software, VMX, doesn't know anything about QCOWs. That's all handled internally by a separate program that VMX doesn't have to worry about. Another pretty big example in Plan 9 is we have DevDraw. We do our graphics through a file-based interface, which means that like our network, you can export and import a graphical stack over the network totally fine, and completely network transparent. The interface I'm giving this talk from, DrawTerm, actually works by creating a file system that it exposes to a remote host that translates these draw calls to how they're used on a local machine, so a Linux or Windows or Mac OS machine, then translates those draw calls in order to create a local interface on top of this. We have SSHNet, which is another really great example. People, it's quite often people use stuff like SSH forwarding, but what if we could just borrow an entire /net? We can do that. So with SSHNet, you connect to a remote machine, you establish an SSH connection, and then anything that is done through the /net that is exposed is actually transparently tunneled to the remote machine without having to do any sort of extra magic. So you can kind of not only can you use this R import trick for machines that are running Plan 9, you can also use this trick for machines that are running Unix as well, completely transparently. So in this overall, like a large chunk of programs that we use in Plan 9 are kind of based around this core idea. A lot of the way that we separate programs, isolate responsibilities, is all done through this file-based interface. So that kind of wraps up the basics of this for this video. As a recap, Plan 9 prefers putting interfaces on the file system. This allows us a great deal of flexibility with these interfaces, so we can manipulate and combine them together. These interfaces can easily be wielded by both the shell and C, and any other language if you happen to port one, without having to add a bunch of extra system calls to accommodate these features. And this design influences a large chunk of the system and how it works together, how we separate things. So that's it for this video. We'll be talking next time mostly probably about namespaces and how those work and process ways in which processes separate from each other. But thanks for watching, and have a great rest of your day.